we were asked to evaluate the line integral along the curve C of f dot differential r, where the vector field f is given and the curve C is the circle of radius 4 centered at the origin, parameterized in the counterclockwise direction as shown here. Remember, we can think of the value of this line integral as the amount of work the given vector field or force field does on a particle as it travels around the circle or the curve C in the counterclockwise direction. Looking at this graphically, the vector field or force field is graphed in purple and the curve C is graphed in red. If we follow this blue point around the circle in a counterclockwise direction, again the value of the line integral would be the amount of work the force field or vector field does on the particle. Going back to our work, we evaluated this line integral earlier using this definition of a line integral, but now that we've learned about Green's theorem, we can evaluate the line integral in a much easier way. Let's begin by reviewing Green's theorem. Green's theorem states that if the curve C is a simply connected piecewise smooth curve with a positive or counterclockwise orientation that encloses a region R, then if the vector field F has an x component of P and a y component of Q, and P and Q have continuous first-order partial derivatives, then the line integral along the curve C of f dot differential r is equal to the double integral over the region R of the partial derivative of Q with respect to x minus the partial derivative of P with respect to y differential A. So going back to our first slide, this red curve is the curve C, and the enclosed region, the circle, is the region R. For the vector field F, P is equal to 3x minus y, and Q is equal to x plus 5y. So because Green's theorem is satisfied here, we can evaluate the line integral using this double integral over the region R. So the given line integral along the curve C of f dot differential r is equal to the double integral over the region R of, and now let's find the difference of these partial derivatives. The partial derivative of Q with respect to x is going to be 1. Remember, we differentiate Q with respect to x, treating y as a constant. And then we have minus the partial derivative of P with respect to y. Now we differentiate P with respect to y, treating x as a constant. The partial P with respect to y is negative 1. And then we have differential A. 1 minus negative 1 is 2. So now we have the double integral, where the integrand function is now just 2. But because the region R is a circle, let's use polar coordinates to evaluate this double integral. Using polar coordinates, differential A is equal to r dr d theta. And now for the region R, the radius is going to be from 0 to 4. And then for theta, because we went the entire circle, theta will be from 0 to 2 pi. The value of this double integral is the same as the value of the line integral. We begin by integrating 2r with respect to r, which would be 2 times r squared divided by 2, which simplifies to r squared. Now we find big F of b minus big F of a, which would be 4 squared minus 0 squared, which is 16, giving us the integral from 0 to 2 pi of 16 d theta. And now we integrate 16 with respect to theta, which gives us 16 theta. And now we find big F of b minus big F of a one more time. Factoring out the 16, we have 16 times the quantity 2 pi minus 0, which gives us 16 times 2 pi, which is equal to 32 pi, which is the same value we found in the previous video using this definition of the line integral. And again, we can think of this value as the amount of work the force field does on a particle as it travels around the curve C with a counterclockwise orientation. Let's go back to the graph one last time. Again, we can think of 32 pi as the amount of work the force field or vector field does on this blue particle as it travels around the circle in the counterclockwise direction. I hope you found this helpful.